Hi everybody and welcome to our Pacific Quasiworld today. Our first speaker is Hiroki Sumi and he will talk about random dynamical systems of complex generalized Henon maps. Please, Hiroki.
Okay, so thank you very much for introduction. So I'd like to first of all, I'd like to thank the organizers for giving me this opportunity. And I will talk about the random dynamical systems of complex generalized Henon maps. So that's the topic of random iteration. So the motivation is as follows. So nature has a lot of random or noise terms. So thus it is natural and important to consider random dynamical systems. On the other hand, holomorphic dynamical systems have been deeply investigated. The study of them helps us to investigate real dynamical systems somehow. And combining the above two ideas, we consider random holomorphic dynamical systems. And we want to find new phenomena, so-called randomness-induced phenomena in random dynamical systems, which cannot hold in deterministic iteration dynamical systems of single maps. There are several other motivations. One of them is the random relaxed Newton's method, in which we can find roots of polynomials f of z more easily than the deterministic methods in a sense. Here we have a polynomial f of z in one variable, and we want to find the roots of this polynomial, and we consider the random rational map z2 z minus lambda times fz divided by the derivative f of z. Here, lambda is a random number uniformly chosen in the disk with center 1 and radius r. Here, r is a non-random number between 1/2 and 1. And we consider the random iteration of these guys. Then we can show that for all but finally initial values, for almost every sequence of these random maps, the orbit tends to one of the root of f of z. And actually, if you consider the usual iteration dynamical systems of a Newton's method or a relative thing, we cannot have such a kind of thing. So there are lots of couple of f and z naught, initial value z naught, for which we cannot find the root. So here we found benefit from the randomness. We want to find such a kind of thing sometimes. Okay, that's the randomness-induced phenomena, a kind of randomness-induced phenomena benefit. Okay, and this was already published in the CMP, and there are another motivations. One of them is the there are other motivations. One of them is the action of holomorphic automorphisms on complex manifolds, and the action of mapping class groups of the Riemann surfaces on the character varieties, etc. Some researchers say Serge Kanter and other persons are working on it. Okay, so those are the motivations. And so here comes some definitions and notations. Let's see to be the two-dimensional complex Euclidean space, and let f be a polynomial map on C2. That is, if we write f of xy equal to g of xy and h of xy, then g of xy and h of xy are polynomials of x and y. And we say that f is a polynomial automorphism on C2 if f is a holomorphic automorphism on C2. And let PAC2 be the space of all polynomial automorphism on C2. Then here is some remark. If f belongs to PAC2, then the inverse of f also belongs to PAC2. Okay. And here are some remarks. If f belongs to PAC2, then f is conjugate by an element g in PAC2 to one of the following maps. A, an affine map of this form, and B, an elementary map of this form, and C, a finite composition of some generalized Henon maps of this form, xy to y, p of y minus delta x, where delta is a non-zero number, non-zero complex number, and p of y is a polynomial of y with degree p, with degree 2 or more. So the final one, the third one, C, is the interesting to see, and we want to consider the random iteration of these guys. Okay. So in order to consider that kind of thing, we want to consider the following. So let X plus be the space of all maps F of the form f of x y equal to y plus alpha, p of y minus delta x, where alpha is a complex number and delta is a non-zero complex number, and p of y is a polynomial of y with degree 2 or more. Note that x plus is included in PAC2. So PAC2 was the space of all polynomial automorphism on C2. Okay. And we endow x plus with the topology such that a sequence fjxy equal to y plus alpha j, pj of y minus delta jx in x plus converges to an element f of xy equal to y plus alpha, p of y minus delta x in x plus, if and only if 1 alpha j tends to alpha, and delta j tends to delta, and degree of pj is equal to degree of p for each large number j, and for the coefficients of pj converge to the coefficients of p appropriately as j tends to infinity. Okay, also we set x minus the set of f inverse in PAC2 where f runs over x plus, endowed with the topology similar to that of x plus. And note that x minus is canonically isomorphic to x plus via this correspondence. Okay, so x plus is a countable disjoint union of finite dimensional complex manifolds. Okay, and here are some remarks. If f belongs to x plus or x minus, then f is conjugate to a generalized Henon map by an element G in PAC2. And second, if f belongs to x plus, respectively x minus, then f can be extended to a holomorphic self-map on P2 minus 100. Point 100 is the one point in P2. Okay, respectively P2 minus 010. And 3, for each f in x plus, respectively x minus, the point 010, respectively 100, is an attracting fixed point of f. So here, if you have one element f in x plus, then if you have any element f in x plus, then this point 010 is a common attracting fixed point of f. Okay, and this point 100 is a common attracting fixed point of f inverse. Whatever f is, whatever the element f in x plus is, okay? Since f inverse is, if f belongs to x plus, then f inverse belongs to x minus, okay? And let M1x plus, respectively M1x minus, be the space of all Borel probability measures on x plus, respectively x minus. Also, we set M1cx plus, respectively M1cx minus, the set of all elements tau in M1x plus, respectively M1x minus, for which the support of tau, that is the topological support of tau, is a compact subset of x plus, respectively x minus. And we endow M1cx plus, respectively M1cx minus, with the topology O, which satisfies that the sequence tau n tends to tau as n tends to infinity, if and only if A. For each bounded continuous function phi on x plus, respectively x minus, we have that the integral of phi with respect to the measure tau n tends to the integral of phi with respect to the measure tau as n tends to infinity. That is the thing from that is the weak star convergence thing, and the second and one other one, support of tau n. That is a non-negative complex subset of x plus, respectively M1x, respectively x minus, tends to the support of tau. That is also a non-relatively complex subset of x plus, respectively x minus. Ascent tends to infinity with respect to the Hausdorff metric in the space of all non-relatively complex subsets of x plus, respectively x minus. I think this is a natural topology. So this one is a weak circumvergence thing, and this one is a the convergence thing coming from the convergence of the support of the noise. Okay. This one, only this, if you have only this one, then it's a little bit too nasty, and I want to add this one, this kind of thing. Okay. And from now on, for each tau in M6 plus, we consider independent and identically distributed random dynamical system on P2 minus 100, such that at every step we choose a map F in X plus according to tau. This defines the Markov process whose state space is P2 minus 100 and whose transition probability P of Z A from a point Z in P2 minus 100 to a Borel subset A of P2 minus 100 satisfies P of Z A equal to is equal to tau of the set of elements F in X plus for which F of Z belongs to A. The easiest thing is the following. So here you have two maps F and G, and you map and you have a dice, and you throw a dice, and you choose first you have an initial value Z naught, and you have a dice, and you throw a dice, and if you get the odd number, and then you choose the first map F, and you map the point, you map the initial value under the chosen map F. And if you get the even number, then you choose another map G, and you map the initial value under the chosen map G. Okay? And then after that, you throw a dice again, and you continue this procedure over and over again. This is the random iteration. Okay, the easiest thing, the easiest situation is this. Okay, and now we want to consider this kind of thing, and we want to, in order to investigate that kind of thing, we have to consider the following. So for each tau in MNC X plus or MNC X minus, let G tau be the set of all finite compositions of elements of support of tau. That is a semigroup. This is a semigroup with the semigroup operation being the functional composition. Actually, this is a semigroup, but not a group, so we have to be careful. Okay. And so this is a very natural thing to consider in order to analyze this IID random dynamical systems on P2 minus 100 generated by this tau. Okay. Okay. And then we want to introduce a nice class of random dynamical system. In order to do that, we need the following notation. Let lambda be an open subset of P2, and we say that an element tau in M6 plus or M6 minus is mean stable on lambda if each f belongs to support of tau, if each f in support of tau is defined on lambda, and f of lambda is included in lambda, and there exists a positive integer n, a positive integer m, a non-empty open subsets u1 blah 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 u1 of lambda, a non-empty complex subset k of union of uj, and a constant c with 0 less than c less than 1, such that the following a and b hold. A. For each gamma 1 blah 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 gamma n in support of tau to the power n, we have the gamma n blah 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 gamma 1 of union uj is included in K. So the figure is as follows. So here you have finite open subsets U1 blah blah UN, and inside in it we have a blue part that's a K. That's a finite. That's a complex subset of a union of uj. And if you consider that finite n words, if you consider the n words, of support of tau, then the image of union of uj under this one is included in this blue part and the compact subset of union of uj. Okay, and moreover, for each j equal to 1 to m, and for all x and y in union uj, and for each gamma 1 blah blah gamma n in support of tau to the power n, we have the distance between gamma n blah 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 gamma 1 of x and gamma n blah 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 gamma 1 of y is less than or equal to the constant c, this c, times distance between x and y. So this finite this n words gamma n blah blah gamma n is a contraction in this region. So if you have a initial value here, then we have a contraction phenomena. So the situation, the dynamics is very mild in this region. Okay. And B, for each z in lambda, there exists an element f sub z in g tau. G tau was the semigroup generated by the support of tau. Oh, let me see. This one. Okay. And such that f sub z of z belongs to the union of uj. So it means that here we have a picture. Here we have a initial value z, and there exists. So this might be a nasty initial value for some map in the system, but this regarding this, for this initial value z, there's a very nice element f sub z, kind of teacher for this guy, f sub z in g tau, and this f sub z carries this point into this nice region u sub 1 blah blah um. And once we have the point here, we have a contraction phenomena, a contraction thing. So the situation, the dynamics is very mild. Okay. So this is a definition of mean stability on lambda. So the situation is very mild. Maybe you may think. Okay. And we want to consider the following. Let MS be the set of all elements tau in M1CX plus, satisfying that 1. Tau is mean stable on P2 minus 100. So tau is mean stable on P2 minus 100. Here lambda is P2 minus 100. And tau inverse is mean stable on P2 minus 010, where tau inverse is the element of M1CX minus, such that the tau inverse of A is equal to the tau of the set of elements F in X plus, for which F inverse belongs to A, for each Borel subset A of X minus. Okay, and we can easily show that this set MS, this one is a subset of M1CX plus, and we can easily show that MS is open in M1CX plus. So this is the topological space. Here, O was the topology induced here. Okay, so weak stir convergence of the measures and plus and the convergence thing, plus the thing from the convergence of the support of the measure. Okay. Okay, so this is easy to show that it's easy to show that this one is open in M1CX plus O. But the people might think that since this condition is very, very strong, you know, P2 minus 100 is the whole phase space. So mean stability on the whole phase space is very, very strong. So people might think that it might be empty. Okay, if this one is empty, then there's nothing to consider. Okay, here we please check the mean stability on P2 minus 100 or 100. Okay, but actually we can show that this MS is dense in M1CX plus O. Actually, By the way, so if you consider the direct measure at one complex generalized Henon map, then that kind of direct measure doesn't belong to this set MS. We can easily show that. And so actually, we can show that MS is open and dense in MSX plus all. That's the first result. So here comes the main theorem, the first main theorem. MS is open and dense in MSX plus all in this topological space. And moreover, for each tau in MS, we have all of the following statements 1 to 5. 1. There exists a negative constant C tau such that the following holds. For each initial value Z in P2 minus 100, this was the phase space, there exists a Boyle subset B tau Z plus of X plus to the set of integers with infinite product of tau of P tau Z plus equal to 1, such that for each gamma equal to gamma J in B tau Z plus, we have a lim sup of the 1 over n times log of the norm of the derivative of gamma n minus 1 blah 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 gamma naught at Z is less than or equal to this negative constant C tau. So for each initial value Z and for almost every sequence, the maximal Lyapunov exponent is negative. Okay. And the similar thing for backward dynamics. Actually, I mean, also for each Z in P2 minus 010, there exists a Boyle subset B tau Z minus of X plus to the set of integers with infinite product of tau of B tau Z minus equal to 1, such that for each gamma equal to gamma J in B tau Z minus, we have a lim sup of 1 over n times log of the norm of the derivative of inverse of gamma minus n, blah, 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 inverse of gamma minus 1 at Z is less than or equal to this negative constant C tau. So here, for each rational map F on P2 and for each Z in P2, where if it's defined, we denote by this one the norm of the differential of F at Z with respect to the Fibonacci metric on P2. So whatever the metric is, whatever the Riemannian metric is, that's okay. Anyway, so for regarding the forward dynamics and backward dynamics, for each initial value Z in the phase space, for almost every sequence, the maximal Lyapunov exponent is negative. Okay, so that's the first result. And that's the first statement 1. By the way, if you consider the usual iteration dynamics of a single complex generalized Henon map, this cannot hold, because if you take a point Z in the Julia set, if you take a point Z in the periodic saddle, then this cannot hold. And there are lots of there are infinitely many periodic saddle, at least, you know. So this is a new phenomenon in a sense in the random dynamical systems. And the second statement, for each Z in the P2 minus 100, the phase space, there exists a Borel subset C tau Z plus of X plus to the set of integers with infinite product of tau of C tau Z plus equal to 1, such that for each gamma equal to gamma J in C tau Z plus, there exists a positive number R plus, which depends on tau, Z, and gamma, satisfying that the diameter of the gamma n minus 1 blah 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 gamma naught of BZR plus tends to 0 as tends to infinity. So like this. So for each initial value Z, for almost every sequence, the forward images shrink along the orbit. And a similar thing for backward dynamics. By the way, so this kind of thing cannot hold for usual iteration dynamics of a single complex generalized Henon map, because if you take a point Z in the Julia set, say, periodic saddle, then this cannot hold. So this also is a new phenomena in random dynamical systems. And the similar thing for the backward dynamics. For each Z in P2 minus 010, there exists the Borel subset C tau Z minus of X plus to the set of integers with infinite product of tau of C tau Z minus equal to 1, such that for each gamma equal to gamma J in C tau Z minus, there exists a number, positive number or minus, which depends on tau z gamma, satisfying that the diameter of the gamma inverse of the gamma minus n, blah, 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 the inverse of gamma minus 1 of b of z r minus tends to 0 as n tends to infinity. So here, the figure is like this. So here you have an initial value z, and if you consider the backward images, then the diameter shrinks. The diameter shrinks, okay, along the orbit, along the backward orbit, okay? Where BZR denotes the ball with center Z and radius R with respect to the distance D induced by the Fibonacci metric on P2. So whatever the Riemann metric is, that's okay. And for each subset A of P2, we set diameter A, the diameter of A. Okay. So this is also this also describes the new phenomena in random dynamical systems of complex generalized Henon maps and their conjugates. Okay. And the third statement, let min tau be the set of all minimal sets of tau in P2 minus 100. Then this one is a finite set. Actually, this one is not empty because the point 010 is a common attracting fixed point of any element in support of tau. Okay. So what I want to say here is that this one is a finite set. Here, a non-empty complex subset L of P2 minus 100 is said to be a minimal set of tau if L is equal to the closure of the zeta orbit of Z for each Z in L. This one cannot hold for usual iteration dynamics of a single complex generalized Henon map because there are infinitely many periodic saddles, you know. And B, for each initial value Z in P2 minus 100, for infinite product of tau almost every gamma j in X plus the set of integers, we have that the distance between gamma n minus 1 blah 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 gamma naught of Z and the union of minimal sets of tau tends to 0 as tends to infinity. So since minimal set, there are only finitely minimal sets, so this sequence tends to one of the minimal set. This one also cannot hold for a usual iteration dynamics of a single complex generalized Henon map because if you take a point Z in the say Julia set and in the chaotic part, that kind of thing cannot hold. Okay, so this one also is a new phenomena in random dynamical system. And fourth statement, for each minimal set L of tau, min tau was the set of minimal sets of tau, and the non-empty complex subset L of P2 minus 100 is said to be a minimal set of L tau if L is equal to the closure of the zeta orbit of Z. Zeta was the semigroup generated by the support of tau. Okay. And let TL tau be the function of probability of tending to one minimal set L. That is, for each initial value Z in P2 minus 100, we set TL tau Z, the infinite product of tau of the set of elements gamma j in X plus to the set of positive integers, for which distance between gamma n blah 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 gamma 1 of Z and L tends to 0 as n tends to infinity. Okay. Then TL tau is locally held or continuous on P2 minus 100. We have this one is continuous. And by the way, this one is also a new phenomena in random dynamical systems. If you if you consider that random usual iteration dynamics of a single complex generalized Henon map, then this kind of function takes a value only in 0 and 1. Only either the value is either 0 or 1. So this one is not continuous on the whole phase space. In the Julia set, this one is not continuous for usual iteration dynamics of a single complex generalized Henon map. Also, TL tau is constant on each connected component of the Fatou set of the same group G tau. Here, f of G tau, this is called a Fatou set of the semigroup G tau, denotes the set of points G in P2 minus 100, for which there exists a neighborhood U of Z such that the semi-UFG tau is equicontinuous on U with respect to the distance induced by the Fibonacci metric on P2. I mean, so this one is a Fatou set of semi-UFG tau, and in other words, this Helder continuous function, this continuous function TL tau is a function which varies only inside the Julia set of the same UFG tau. Julia set is the complement of the Fatou set F of G tau. Okay, that's a little bit complicated thing, you know. Okay, and this was the fourth statement, and the fifth statement is the following. For each gamma in equal to gamma j in x plus to the set of integers, let f gamma plus be the set of elements z in P2 minus 1, 0, 0, for which there exists the neighborhood U of Z in P2 minus 1, 0, 0, such that gamma n minus 1, blah, 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 gamma naught, the sequence of this one, is equicontinuous on U. And similarly, let F gamma minus be the set of elements Z in P2 minus 0, 1, 0, for which there exists the neighborhood U of Z in P2 minus 0, 1, 0, such that the inverse of the sequence gamma inverse of the sequence of inverse of gamma minus n, blah, 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 the inverse of gamma minus 1 on U is equicontinuous on U. Also, let J gamma plus be the complement of F gamma plus, and J gamma minus be the complement of F gamma minus. This is called the Julia set of the sequence gamma. Then there exists the Borel subset d tau of the x plus to the set of integers with infinite product of tau of d tau equal to 1, such that for each gamma in d tau, we have the 4-dimensional Lebesgue measure of J gamma plus and the 4-dimensional Lebesgue measure of the J gamma minus are equal to 0. Leb4 denotes the 4-dimensional Lebesgue measure on P2. And here is an important remark, and none of statements 1, 2, 3, 4 in theorem 3 can hold for deterministic dynamics of a single element f in x plus or x minus. So again, the statement 1 is this one. For almost every sequence, for each z in the phase space, for almost every sequence, the maximal neighborhood of exponent is negative. And the backward dynamics has the similar thing for backward dynamics. And the second, for each initial value z in the phase space, for almost every sequence, the images, the forward images shrink along the orbit. A similar thing for backward dynamics. And 3, there are only finitely minimal sets, and for each initial value z, for almost every sequence, the orbit tends to one of the minimal sets. And 4, the function of probability of tending to one minimal set is continuous. Actually, we can show that this one is locally Helder continuous on the phase space. Okay, that kind of thing cannot hold for usual iteration dynamical system for a single complex generalized Henon map. So we found new phenomena in random dynamical systems. Okay. In my mind, we can say that we have more milder situation than the usual iteration dynamics of a single complex generalized Henon map. So we want to call it the randomness induced order. Okay, we will call that kind of thing later. And to prove the density of MS in by the way, so this kind of phenomena are generic because the MS is open dense in M1CX plus all. Okay. And to prove the density of MS in M1CX plus in theorem 3, we need the following. So we have to consider the bifurcation of a family of elements of M1CX plus. So let tau t be a family of elements of M1CX plus such that all of the following 1, 2, 3 hold. 1, t to tau t in M1CX plus is continuous with respect to the topology O. Topology O was the this one, okay? And the second, if T1, T2 are elements in the one interval and the T1 is less than T2, then the support of tau T1 is included in interior of support of tau T2. Here, int denotes the set of interior points with respect to the topology in X plus. And three, an interior of support of tau naught is not empty. And let B be the set of elements T in the one interval for which tau T is not mean stable on P2 minus 100. So the definition of mean stability on P2 minus 100 is this one. So please consider the please consider the case that the lambda is equal to P2 minus 100. Okay. Then this set B is called a bifurcation, the set of bifurcation parameters. Then we can show that this B is a finite. B is finite. Actually, the cardinality of B is less than or equal to the cardinality of min tau naught minus 1, which is finite. So there are only finitely many bifurcation parameters in this Z1 interval for this family. Okay, and C, let us denote by C the set of elements T in Z1 interval for which S to the cardinality of min tau S is constant in the neighborhood of T. Then C shows that C satisfies that C is equal to Z1 interval minus B. Okay, so from this theorem, we can show the density of MS. Let we take a general element tau in MS6 plus, and first we approximate this tau by element lol in MS6 plus, such that the support of lol is finite. Then we can construct a family enlarging the support of lol. We can construct this kind of family tau T. Then if T is positive and very small, then the tau T is mean stable on P2 minus 100 from this theorem. So we can find a mean stable element tau T, which is very close to the original element tau in M6 plus. So which shows that the density of MS in MS6 plus O. Okay, that's the rough idea of the proof of the density of MS in MS6 plus O. Okay, and this was a kind of bifurcation thing. And the next one. So what happens if you have a point T in B? What can we say about the tau T with T in B? Okay, that's a little bit nasty guy, but we can still show a nice thing for this tau T. Even for tau T with T in B in theorem 5, note that such a tau T is not mean stable on P2 minus 100. So that's a little bit nasty guy, but we have the following result. Theorem 6, let tau be an element MSC X plus such that the interior of support of W is not empty. Here, int denotes the set of interior points with respect to the topology in X plus. Then tau satisfies the statement 2 to 5 in theorem 3. So let us recall that 2 to 5. So this one is the 2. So that for each initial value z in the phase space for almost every sequence, the forward images shrink. The same, okay. And the 3 was this one. There are only finitely many minimal sets. And 4, for each minimal set L, the function of probability of tending to L is locally held continuous on the phase space. And 5, the forward Julia set and the backward Julia set for any for almost every sequence gamma is of measure 0. Okay. Okay. So we still have a nice thing for such a even if T belongs to B, even for tau T with T in B in theorem 5. Okay. And to prove theorem 6, we need the following theorems 7 and 8. theorem 7, let tau be an element in M6 plus such that the interior of support of tau is not empty. Then tau is nicely absorbing. That is, there exist finitely many open subsets U1 blah 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 UM of P2 minus 100 such that all of the following conditions A, B, C hold. A. U1 is a neighborhood of 0, 1, 0 in P2 such that f of U1 is included in U1 for each f in G tau. G tau was the semigroup generated by support of tau, and such that for each gamma equal to gamma j in support of tau to the set of positive integers, gamma n blah 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 gamma 1 of z tends to the point 0, 1, 0, ascend tends to infinity uniformly on z gamma in U1 times support of tau to the set of integers, positive integers, and B, for each j equal to 2 to m, uj is a bounded open subset of C2, satisfying all of the following conditions 1 to 2. 1. F of uj is included in uj for each j equal to 2 to m, and for each f in g tau. G tau was the semigroup generated by G tau was the semigroup generated by support of tau. And second, for each j equal to 2 to m, there exists a nice map hj in g tau with hj of the closure of uj is included in uj. Okay, like this. Okay, and C, for each z in P2 minus 100, there exists a nice map f sub z in g tau such that f sub z of z belongs to the union of uj. Note that m might be equal to 1. So this situation is similar to mean stability on P2 minus 100, but a little bit different. So, you know. So here, K was the complex subset of union of uj, but here, f of uj might not be a relative complex subset of uj. Okay. Oh, oops. So we can show that if means tau is mean stable on P2 minus 100, then tau is nicely absorbing, but the converse is not true in general. And the theorem 8 is that the following. So if tau belongs to M6 plus and is nicely absorbing, then tau satisfies the statements for the forward dynamics in 2, 3, 4, and 5 in theorem 3. Again, the statement 2 was this kind of thing. So for each t in P2 minus 100, for almost every sequence gamma, the forward images of the small ball around z tends shrink. Okay, and 3, there are only finitely minimal sets, and for each t in the phase space, for almost every sequence, the orbit tends to one of the minimal set, and for each minimal set L in min tau, for each minimal set L of tau, the function of probability of tending to L is locally held continuous, and forward Julia set and backward Julia set for almost every sequence gamma are of measure 0 with respect to the Lebesgue. Okay, and so here is a remark. If tau belongs to M6 plus and if tau is mean stable on P2 minus 100, then tau is nicely absorbing, but the converse is not true in general. For example, tau if t belongs to B and tau, then tau t in theorem 5 is nicely absorbing but not mean stable on P2 minus 100. So we have seen that even if in the bifurcation parameter we still have a nice property in a sense. Okay. Okay, so here's the summary. We can see that the generic random dynamical system of polynomial automorphisms on C2 having some conditions is mean stable on the phase space. And if a random holomorphic dynamical system on P2 minus 100 is mean stable, then for each initial value z in the phase space, for almost every orbit starting with z, the maximum Lyapunov exponent is negative. Okay. There's no positive, there's no non-negative Lyapunov exponent. And 3, and note that the statement of 2 cannot hold for deterministic dynamics of a single polynomial automorphism of f on C2, which is conjugate to a generalized Henon map by a polynomial automorphism. And the fourth, in the proof of the density of elements tau in M6 plus, which are mean stable on P2 minus 100, the phase space, we consider a family tau T in M6 plus, and we analyze the bifurcation in a sense. And five, even for a tau which is not mean stable, for example, a bifurcation occurs, if interior of the support of tau is not empty, then tau is nicely absorbing and has some order. For example, forward images of small balls around all initial values Z in the phase space shrink almost surely for almost every sequence. And we have seen many randomness-induced phenomena in random dynamical systems which cannot hold for iteration dynamics of single maps. So in this talk, we have seen randomness-induced order. Okay. So, and many kinds of maps in random dynamical system automatically cooperate together to make the chaoticity weaker, in a sense, I would say. We call such phenomena cooperation principle. And even if a random dynamical system has a randomness-induced order, the system still can have some complexity. This is very important, because the function of probability of tending to one minimal set might be very, very complicated. I will show you the picture later. And we have to investigate. So we have to investigate the gradation between chaos and order. We have to investigate the weak chaos, in a sense, you know, for that kind of random dynamical systems having randomness-induced order in random dynamical systems. And the reference is as follows. And this S24 is the preprint, which includes some contents of this talk. Okay. This is submitted. By the way, so I said that even if the random dynamical system has a randomness-induced order, like having like a mean stability on phase space, the system still can have some complexity. What kind of complexity do we have? So I want to show you some pictures. And so this is the picture of one dimension. This is the picture this is the example in one dimension. So here you have two real polynomials, f and g. F is a second iterate of z square or z square minus 1, basilica, and g is the second iterate of z square over 4. Those are real polynomials. And we consider the random iteration of these elements f and g up to coin toss, okay? And for each initial value z, we consider the function, we consider the probability of tending to point to infinity in the Riemann sphere. Then this defines a function defined on the Riemann sphere. And this is the graph of it. This is like a Colosseum, and this is also like a Devil's Staircase. So I decided to call it the Devil's Colosseum. Okay. But by the way, what was the Devil's Staircase? This is it, Devil's Staircase. Okay. This is the original Devil's Staircase, and then this is like a Colosseum. So I call it the Devil's Colosseum. And so this one is so this system has a mean stability on the Riemann sphere, actually, in this case. And this function is Helder continuous on the Riemann sphere. And this function is continuous, but varies precisely on this thin fractal set. This is the Julia set of the semigroup generated by f and g. F was the second iterate of z square minus 1, and the g was the second iterate of z square over 4. This is the Julia set of first one f, basilica, and this is the Julia set of second one g. And in between, there are lots of backward images of these. And this is the semigroup. This is the Julia set of the semigroup generated by f and g. And this function is continuous on the Riemann sphere and varies precisely on this thin fractal set. There are lots of things there are lots of interesting things regarding this kind of thing. So Hausdorff dimension this one. So we can work on we can work on thermodynamic formalism. We can consider the skew product map regarding the random dynamical systems, and we can use the thermodynamic formalism, and we can show that Bowen's formula works for this system. And in this case, the Hausdorff dimension of this guy is strictly less than 2. And if we perturb a little bit, then the Hausdorff dimension moves real analytically. Okay, that kind of thing we can show. And so if you want to consider the pointwise Helder exponent, then we can work on multifractal formalism in this case for this kind of thing. So there are a lot of papers around this kind of thing, and we want to work on the two-dimensional analog of this kind of thing. So if you have a one-dimensional polynomial, then we can easily extend this kind of we can easily extend a one-dimensional polynomial to Henon map, complex Henon map. So then you have a random dynamical system of generalized Henon maps, which is very close to this one-dimensional example. Then we can consider the function of probability of tending to 1.010, Then you can draw the picture like this, and if you consider the complex one-dimensional slice, then you still have the kind of figure. You can try, okay, if you have. And by the way, so you also can you can also use a 3D printer, and you can create. But this is not good. But you can create 3D. This one is, but okay. Anyway, yeah. Anyway, this kind of thing you can create. Yeah, one of our colleagues made it, and so that kind of thing works. So so by the way, so this is Devil's Circus Colosseum, and the upside down figure is like this, and this one is called a fractal wedding cake because everyone says that this one is like a wedding cake, and so upside down figure is the graph of the function of probability of tending to the origin regarding this random dynamical systems. Okay, and we want to consider the two-dimensional analog of this kind of thing. So you have a mean stable random dynamical systems on C2, and the function of probability of tending to 1.010 is Helder continuous, locally Helder continuous, and varies precisely on a very thin fractal set. We can consider such a kind of thing, and it will be very interesting, I think. Okay, and by the way, this was the if you perturb the parameters, then we can have a lot of interesting pictures. By the way, so this was disconnected. By the way, if you perturb a little bit, then we can have a connected Julia set, and then this is the function of probability of tending to infinity, and which varies precisely on this connected Julia set, like this. This is the upside down figure of this one. Okay, so I stop here. Thank you very much for your attention.
Okay, thanks a lot. So let's thank our speaker. And as usual, let me start the discussion here. So are there comments or questions?
Hiroki, can I ask you one question?
Yes.
Yes, excuse me. It's Mark here.
Thank you, Mark.
Yeah, in your second condition of your main theorem, you had these disks whose forward images were shrinking. Yes. Would you expect that to be exponential, or would you expect exponential shrinking to be generic?
If you have a mean stability, then this one converges exponentially fast. Yeah, that's true.
Right.
Yeah. But if you have just weaker condition, that the nicely absorbing thing, then we cannot expect. Yeah.
Okay.
That's a nice question. Yeah.
Thank you.